Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking about perfectly elastic collisions. So this is a continuation of my series of discussions of linear momentum and energy together. So again, in order to get the most out of this video, you need to have already worked through the videos that I've made about work and energy and also about linear momentum and its conservation. If you're using this video to help you in a course, then make sure that you are in the part of the course where you've already at this point covered both energy and energy conservation and introduction to linear momentum and are doing collisions. So what is happening in this video, in the kinds of collisions that we're interested in this video? Well, let's begin by recalling a few pointers. First, we have our linear momentum, which is defined as mass times velocity. Second, we have our kinetic energy, which is 1/2 mv squared. That's translational kinetic energy. Third, we have conservation laws. So the conservation laws basically state the following. First, linear momentum is conserved if there are no outside forces acting on your objects in your system. Second, in an elastic collision, mechanical energy is conserved. Now, practically speaking, the top condition means that the sum of linear momentums initially and the sum of linear momentums finally must be equal. The second condition means that the sum of kinetic energies initially is almost certainly going to be equal to the sum of kinetic energies finally. I say almost certainly because we're kind of assuming that there's no changes in potential energy for the system. Okay, so this is what an elastic collision means. So for two objects, this means that we actually have two equations. Our first equation is the momentum conservation equation, or the linear momentum conservation equation, which is going to say that m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. Our second equation says that 1/2 times mass 1 times v1 initial squared plus 1/2 times mass 2 times v2, the initial speed of object 2 squared, should be equal to 1/2 of mass 1 times mass 1's final speed squared plus 1/2 of mass 2 times v2 final speed squared. So you have here a system with two equations. They're not entirely linear equations because the v terms are squared in the second equation, but they are independent equations, which means in principle that if you're given all the masses and all the initial velocities, you can solve for all the final velocities or both of the final velocities. So typically what you have here is two equations to work with and two unknowns to solve for. Now it's possible to have other conditions added, like maybe you're actually told the initial and final speeds of both objects and you have to solve for the mass. So you'd have two unknown masses. Or maybe you know all the final speeds and you know the masses and you want to solve for the two initial speeds. All of that's valid. Remember that in one dimension, this vector symbol over velocity basically is going to mean it's a positive or a negative term. It might be moving left, it might be moving right. If we go to two dimensions, then it gets a little more complicated because these vectors now have an up-down and a left-right component. And so in a sense, you get two equations from this for the price of 1. This one, however, you only retain one equation, so you need some other condition beyond just these 3 equations to solve for. Let's consider some special cases, a variety of little special cases. So special case number 1 is that one object is either initially or finally at rest. So special case 1. One object initially at rest and one object finally at rest. Okay, so this special case will only really happen if the 2 objects have the same mass. We know that because if they have some other ratio of masses, then either you're not going to be able to balance energy or you're not going to be able to balance momentum. So if this is an elastic collision, then M1 equals M2. And so in principle, this statement right here is enough for you to solve for, say, the mass of the system or the mass of each object and the speed of the system. So we could just say this represents M, and so 1 becomes M, let's say V1 initial equals M V2 final. And this essentially implies that V1 initial is equal to V2 final. You can't, of course, solve for both masses unless some piece of information is given about one or the other mass. The other equation, number 2, would simply become 1/2 M V1 initial squared is equal to 1/2 M V2 final squared. And once again, this reduces to V1 initial equals V2 final. So you'd have to have one more piece of information somewhere, namely like how much mass does one of the objects have, or what's the initial momentum of the system, or something like that, in order to actually solve for numerical values of the masses. Special case number 2, this one is a variation of the original special case. The original special case, something is stopped and something is not. Special case 2 is objects exchange velocities. So we could say like they exchange velocities. And again, the only way that this is going to happen in an elastic collision is, once again, they must have the same mass. Okay, so your equations now will look like this. Number 1 becomes M1 V1. We could even call it M1 V1 plus M2 V2, and this will become M1 V2 plus M2 V1. Our kinetic energy equation would become 1/2 M1 V1 squared plus 1/2 M2 V2 squared is 1/2 M1 V2 squared plus 1/2 M2 V1 squared. And again, it can be shown, although I won't do it, that this will work if mass 1 and mass 2 are both equal to each other. So essentially, if you do that, then all the masses are equal, and so what these will end up becoming is simply V1 plus V2 equals V2 plus V1, and V1 squared plus V2 squared is V2 squared plus V1 squared. That's if all the masses are equal. And that's the only way to make these two conditions both be true simultaneously. All other conditions beyond those end up being essentially kind of non-special conditions, and in this case you basically have to go to your system of equations and solve. And those problems are doable, but they tend to take a lot of time, like more than what I really want to sink into a quick video about this subject. So unless you happen to be given another piece of information like the total energy is so much, and even then you largely have that, because if you're told mass 1, mass 2, v1, v2 at the start, then you know what the initial momentum is, you know what the initial energy is, and therefore you know what the final momentum and final energy are. So there's not much more for me to add to this video at this time beyond a very long example, and I don't really want to do a very long example in what's supposed to be a short video. So thanks for watching as always, and I hope you got something out of today's video. See you in the next one.